Welcome back to the Deep Dive, where we take big stacks of source material and turn them into pure, concentrated knowledge for you.
Today, we are absolutely plunging into one of the most exciting tools in modern development.
We are talking about Flutter, Google's UI framework. If you've heard the hype about building beautiful, native, reactive applications from a single code base, this is your shortcut. This is how you understand the engine.
And our deep dive today is grounded firmly in the fundamentals. We're drawing heavily from Beginning Flutter, a hands-on guide to app development by Marco L. Napoli.
So our mission isn't just to list features, is it?
No, not at all. Our mission is to really deconstruct the core architecture, the principles that make Flutter so powerful for building apps on, well, pretty much every surface. iOS, Android, web, desktop, you name it.
We're going for total clarity here. We're going to look at the Dart language, the tools that just turbocharge your workflow, and crucially, this concept of the three trees that defines the entire architecture.
Let's start with what matters most: speed.
The whole story of Flutter, it really began back in 2015. It was unveiled as Sky. And it was experimental. But the one non-negotiable goal from day one was speed.
Right. The early focus was just Dart on mobile. How do we make it fast and responsive?
Yeah, they were targeting 60 frames per second or 60 hertz, and even pushing for 120 hertz on devices that could handle it. It really seems like they saw the speed limits in other technologies and just said, nope, we have to do better.
And that obsession with speed is precisely why Dart was chosen. Dart's an object-oriented language. It's class-based with a syntax that, well, it feels very familiar if you've ever used Java or C++O or Swift.
Just easy to pick up.
Very approachable. But its real genius structurally is in its dual compilation. It perfectly serves the chaotic needs of development and the really strict demands of a public release.
Okay, explain that twin engine approach, because this feels like where the speed really comes from.
It's just elegant. So for your production release, Dart uses AOT, or ahead of time compilation. It compiles your Dart code directly down to native ARM machine code.
Which is a huge deal.
It's the critical distinction. It's the answer to why are Flutter apps so fast? Because it's native, the code runs directly on the OS. There's no intermediate interpreter, no performance-killing bridge to translate things. It's just pure speed.
Okay, so AOT gives us that blazing, fast release performance. But development is all about iteration. You have to recompile natively every single time you change, like a line of text, you're back to waiting.
You are, and that's the other side of the engine, JIT, or just-in-time compilation. JIT is used only during development and debugging.
Optimized for speed of a different kind.
Exactly, for rapid changes, for fast feedback, and it's what enables Flutter's most famous feature, the stateful hot reload. The language itself makes that revolutionary workflow possible.
So the language solves the speed problem, but what about actually drawing to the screen and making it look good?
That's the rendering engine. Flutter completely sidesteps native UI components. It doesn't use the standard iOS or Android widgets you'd expect.
It does its own thing.
It handles all of its own drawing using the Skia 2D rendering engine. And if that name sounds familiar, it should. It's the same engine used by Chrome, Android, and Firefox.
So by owning that entire drawing process, Flutter can guarantee those high frame rates.
Absolutely. Smooth animations, smooth scrolling, smooth transitions, all of it, even when you're rendering really complex custom UIs.
So if Dart and Skia remove all these performance hurdles, what does that mean for the developer's mindset? I mean, how do we even approach building an interface?
It leads you directly to the core philosophy. Declarative UI. Instead of the old imperative way, find a button, manually change its text.
Right.
Flutter is declarative. The sources make this crystal clear. The UI is just a reflection of the current state of your app. When the state changes, you don't manipulate the screen, you just declare what the new screen should look like, and the framework handles the redrawing for you efficiently.
So you're not modifying the house, you're just handing the builder a new set of blueprints.
That's a perfect way to put it.
And that leads directly into the core building blocks, the widgets.
Indeed. Widgets are the basic unit of composition. The book calls them the Lego blocks of a Flutter app, which is perfect. They're just immutable declarations of the UI. Think of them as configurations or instructions for what something should look like right now.
Okay, let's unpack the architecture that makes this whole thing work, because this is where Flutter gets really clever. When a developer nests these widgets together, a row inside a container, text inside the row, we create the visible widget tree.
Right, but that's only the first of three critical structures.
That's just the blueprint.
It is. It's what you, the developer, create in the code. But below that, the framework immediately steps in to bring that blueprint to life.
Which brings us to tree number 2, the element tree. If the widget tree is the blueprint, I guess the element tree is the construction manager.
That's a great analogy. Elements are the actual widgets mounted on the screen. They're the rendered reality.
Uh-huh.
And the element tree's most important job is comparison. When state changes, it compares the old widget configuration against the new one to figure out the absolute minimal set of changes needed. It's a diffing process that ensures efficiency.
And here's a detail that trips up a lot of newcomers. The build context objects that we use everywhere in Flutter code. Those are actually references to these element objects, right?
That is exactly right. So when you use a build context, you are literally referencing the precise rendered location of your widget on the screen. It knows where it is.
So the element tree maintains the identity of everything.
It does, across rebuilds, which is key to performance. Now, under that, we have the third layer, the render tree.
This is where the physical work happens, the laborers on the construction site.
Correct. This tree uses the low-level render object to compute all the detailed geometry, layout, constraints, size, the actual paint protocols. The crucial point here is that developers almost never interact with the render tree directly.
The element tree handles all the smarts.
Exactly. The element tree does the intelligent comparison and only talks to the render tree when it absolutely has to redraw or reposition something. That abstraction is what keeps it so fast.
Understanding that structure is so important, especially for state. It explains why we have two fundamental types of widgets, stateless and stateful.
And the distinction is simple, but the implications are huge. A stateless widget is, well, it's straightforward. You use it when the configuration and data never change. A static label, a decorative icon.
One class and you're done.
One class. The element tree mounts it, and it stays there until its parent tells it to go away.
But the moment you need to change something, an icon toggles from favorite to unfavorite, text updates from an input field, you need a stateful widget.
And this is where that two-class structure comes in. A stateful widget needs two classes, the main stateful widget class and a separate state class.
Why two?
Because the widget part is still immutable. It's still just a configuration. But the associated state object has a long, persistent lifespan. It holds the mutable data. Even if the framework throws away and rebuilds the widget instance 10 times, that underlying state object holding your actual data persists.
So the widget is the temporary instruction and the state object is the long-term memory.
Perfect. And the key action for the developer is calling the setState method inside that state class. That call is your signal to the framework. It tells the element tree, hey, the data changed, check the blueprints again, compare, and schedule a rebuild.
So the architecture is complex under the hood, but the developer experience is so streamlined, we should probably just acknowledge the basic setup. You need the Flutter SDK, Dart, some IDE plugins, and platform tools like Xcode for iOS.
Right, the initial setup. But once that foundation is laid, the development loop is transformed by the biggest productivity game changer of them all.
We have to talk about stateful hot reload.
Oh, absolutely. We mentioned that JIT compilation enables it, but its real-world impact is. It's just hard to overstate.
This is where it gets really interesting for anyone who struggled with mobile dev in the past. I remember working on old Android apps where a full restart could be 30-45 seconds just to see a text change.
That wait time is exactly what Flutter eliminates. Stateful hot reload injects the updated source code right into the running Dart virtual machine, rebuilding the widget trees in milliseconds.
But the key part is the stateful part. It doesn't reset your app's state.
That's the magic. Give us that counter example from the sources.
Okay, so you have a counter app. You've tapped the button 3 times, the value is 3. Then you realize you want to change the font color of the number.
Right, a simple UI tweak.
You make that change, you hit save, and the app instantly updates the UI without resetting the counter. You are still on the same screen, same scroll position, and the counter value is still 3.
That instantaneous feedback loop, it just turbocharges development speed. It's unlike almost any other cross-platform solution out there.
That retention of state must save developers hours every single day. Now, with a single code base running everywhere, project organization becomes so important. What does the source recommend for folder structures under that main lib directory?
Disciplined separation of concerns is just vital. The sources suggest organizing by functionality. So you have lipages for your main UI screens like a homepage.
Makes sense.
Then lib models for your data classes, lib services for all your external data logic connecting to Firebase, calling a REST API.
And a couple of helpers.
Right, libutils for generic helper functions, and crucially, lib widgets. This is for your reusable UI components that you share across multiple pages. It keeps everything clean.
That structure stops the lib folder from becoming a total mess.
It forces maintainability, which is the long-term goal.
So moving into actually building these UIs, the core design usually starts with the scaffold widget, right? That's the basic material design visual structure.
Correct. The scaffold is your canvas. Within it, you use components like the app bar. It's highly customizable. You can set the leading widget, the title, a list of actions on the right. The sources also mention the flexible space property, which is great for dynamic backgrounds.
And a safety measure you absolutely cannot ignore, the safe area widget.
Mandatory. It's just mandatory in this era of notches and screen cutouts. The safe area widget automatically wraps your content and adds padding to keep it from getting hidden behind the status bar or the iPhone notch.
Forgetting safe area is a fast track to a bad app review.
It really is. And of course, you can't forget the container. It sounds so generic, but it's the workhorse of styling.
They use it for everything.
You do. It can be an invisible placeholder for spacing, or you can use it for really sophisticated styling with colors, borders, shadows, you name it.
Now, let's circle back to that widget tree structure. When developers start nesting things, container in padding in column and row, we hit what the source calls the deep tree dilemma.
This is a huge structural and performance insight from the book. You get this full widget tree from excessive nesting, and while it works, it makes the code unreadable. You're just scrolling endlessly.
And it hurts performance.
It does, because the framework has to process this massive tree every time a small state update happens high up in the hierarchy.
So the goal is to create a shallow widget tree. How do we do that? The sources outline two refactoring techniques, but one is clearly better for performance.
The first is method refactoring. You separate complex UI into private Dart methods, like build header image. This definitely improves readability.
It cleans up the code, but you said there's a performance drawback.
There is. These methods are tied directly to the parent widget's build context. They run as part of the parent's build method. So if the parent widget redraws, all of those methods get executed again, even if their output hasn't changed.
So you've cleaned up the code, but you haven't optimized the rebuilds.
Exactly. We need a method that helps with both readability and performance.
And that would be
Widget class refactoring. This is the key best practice. Instead of methods, you separate UI segments into their own dedicated stateless widget classes. For example, a user profile avatar widget.
why is making it a separate class so much better than just a method?
It all boils down to caching and the element tree. When you call these new widget classes using the const keyword like const user profile avatar, you're telling the framework two very powerful things. First, this widget and its children are immutable. And second, the framework can now build and cache that widget once.
So when the parent widget rebuilds, if the framework sees const user profile avatar, it knows it can just skip that entire subtree.
Exactly. It leverages Flutter's internal subtree rebuilding. The element tree sees the configuration hasn't changed because of const, so it avoids calling the build method entirely. Only the parts that genuinely change state get redrawn.
That is such a fundamental insight. Use dedicated const widget classes for static UI, not methods. That's the foundation of a performant app.
It really is.
Okay, so we've had a really comprehensive deep dive into Flutter's foundations. We covered Dart's AOT and JIT compilation, the three architectural trees, widget, element, and render. And we landed on the absolute importance of a shallow widget tree for performance.
And before we close, we have to talk about something crucial for production. External packages. They come in two main types. You have Dart packages, which are pure Dart logic, platform agnostic.
And then you have plugin packages.
Right. And the plugins are what connect the Flutter world to the native OS. They include a Dart API alongside native code Kotlin for Android, Swift for iOS that lets you access platform features.
Like the GPS or the camera.
Or payment systems, Firebase integration, shared preferences. They are enormous time savers. You skip writing tons of native code and just focus on your app's logic.
They are the definition of developer productivity.
They offer tremendous initial speed, but they do come with a systemic risk.
And that leads us to our final thought for you. While external packages are incredibly productive, they save you time, thousands of lines of code. They introduce an inevitable reliance on external authors. You're counting on others to fix bugs, to maintain the native code every time Apple or Google changes its OS.
Which raises a really important question for any serious project. How much long-term maintenance dependency are you comfortable accepting in exchange for that initial speed and productivity gain? It's a trade-off every single developer has to constantly evaluate.